Welcome to our presentation for our Magnetic Levitation System semester project. Our group members include Elizabeth Turner, Jacob Colquitt, Ben Sires, and Walker Nunes. Let's get started. Our goal for this project was to build a device capable of magnetically levitating a lightweight metallic object. A force produced by an electromagnet placed above the object would balance the effects of gravity. Using a sensor to determine the position of the object, we can vary the current going through the electromagnet in order to ensure the relative distance between the object and magnet is constant. The object should appear to hover in place. Our system components started with the solenoid, a 12-volt electric lifting magnet with an overall lifting capacity of 250 newtons. The object we chose to levitate was a pink refrigerator magnet based off of its light weight and symmetry. Up next is an IRF 540 transistor MOSFET to act as the on-off switch for the current, followed by a 1000 volt diode for directing current flow. We also have a 1000 ohm resistor used in the circuit to manipulate magnitudes of voltage and current. We have an LED bulb used in the design process to indicate where current is flowing and a Hall sensor for proximity sensing. Our frame and supports were built out of 1 by 4 inch wood boards. At the top, a space was left in between the supports for the electromagnet to sit. One of our team members 3D printed a custom mounting bracket to be screwed into the top of the supports and hold the electromagnet in place. A hole was added to the back of the solenoid mount for the wires to exit and run down the back frame support wall. The base was cut from a larger piece of wood and can be removed if needed. Here you can see our final product design, as well as a close-up of our mounted breadboard and inner workings. Let's now take a closer look at the complex math behind all of this. For the current, notated as I, the solenoid will impart an attractive force on the object. N is the number of coil turns, mu is the magnetic permittivity of the environment, Y is the distance between the solenoid and the object, and M is a positive term to denote that the dipole moments are aligned. To find the transfer function, we began with a free body diagram of the levitated object and wrote an equation for the summation of forces, including the force of gravity, acting on the object. We can substitute the left side of the equation using Newton's second law to reach the equation listed next to number 2. To achieve steady state, the gravity constant can be set to 0 because of the presence of the opposing magnetic force. We are left with a nonlinear function which represents the small controls that maintain this steady state. After linearizing and taking the Laplace transform of the function, we reach our final equation, which describes the relationship between the current I and distance y between the solenoid and levitated object. Since we are operating our levitator on an analog system, the Hall sensor will measure the position of our object and control the voltage to the solenoid. When a magnetic object is near the sensor, the voltage of the system is disengaged and is engaged by removal of the magnetic object. The solenoid will naturally create its own magnetic field when power is running through it. The magnetic field can come in contact with and have an effect on the magnetic field of the levitated object. We have chosen to ignore this possible effect, while also placing the Hall sensor near the solenoid and above the object. In order to test the functionality of the sensor, we set up a breadboard with a linear Hall sensor, a 1000 ohm resistor, a magnet, a power source, and a multimeter. You can see the sensor, resistor, and appropriate wiring in this image. The power source was activated and set to 7 volts. When the magnet was placed in close proximity to the sensor, the voltage on the multimeter read 0 volts. When the magnet was removed, the voltage read 7 volts. This, of course, indicated that the sensor was functioning correctly. This small success did not come without a price. We experienced a lot of difficulty getting the sensor and accompanying circuit to operate properly. Some of our group members spent countless hours of troubleshooting while attempting to correctly orient the circuit and determine which piece was faulty. Unfortunately, many sensors, LED bulbs, and resistors were lost in these testings. As we learned in class, poles have to be to the left of the imaginary axis on the S-plane to be considered stable. Analyzing our transfer function shown in the top image, the location of the poles is as shown to the right. In this case, the system is inherently unstable. In order to stabilize the system, a PD controller was implemented. Analyzing the PD controller, we found the damping needs to be greater than 0.69, the natural frequency must be greater than 28.9 radians per second, Kp must be greater than 13, and Kd must be greater than 0.142. Here you can see our theoretical as well as our actual final breadboard assemblies. Up next, we will attempt to demonstrate the functionality of our system.
So this is our Hall sensor, and then we've got our control circuit here. What we're showing is the magnetic force turning off once we put a magnet up to our Hall sensor. So there we go, it came off, and now it's stuck back again. So we'll demonstrate it one more time. And it drops free.
We were unable to obtain footage of our finished levitator working properly. In our final attempts, we held the levitating object close to the solenoid and sensor and experienced some movement and fluctuation. Immediately as we let go of the magnet, the object will cling to the electromagnet. So we could not necessarily see the effect of the sensor or capture it on video, but we could feel it. This could have been for a plethora of different reasons, such as our choice in magnet, levitating object, placement of the Hall sensor, or even a fried or faulty component on our breadboard. We were unable to troubleshoot thoroughly due to our strict deadlines and had no choice but to leave the project as is. Thank you.